Okay, thanks very much. So just this project is the Westown Square down in KZN. So the project was we finished the project sort of halfway through last year, and our scope on this project, we were fortunate to have two bits of work on this project. One is a feature canopy that you're looking at now, and then the other part is a stage canopy. So the client on this project was Fundamentum. So they were in charge of the whole development, which the center is just one part of it. There's other parts that are still going to get built. There were two architects, MDS, and then also Bookman and partners down in KZN, and the main contractor was definitely Stocks. So Leaf Structures, we were subcontracted under the main contractor. So Leaf Structures, our responsibility was design, supply, and install of these two canopies. So you can see the one kind of in the background is this feature canopy, and the purpose of it, they've got a nice lawns area, they've got a nice playground, and then so to the right of it, they've got this big barn structure, which is quite a nice, quite a large volume place where there's a lot of restaurants and entertainment. And then on the left, there is more like regular shops that run throughout the mall. So the feature canopy was there to kind of bring all these parts together. So first of all, so you can see where the entrance is, but also you've got all these interesting geometries and interesting applications. So it's trying to blend those. The other thing, which you can't quite see from this picture, but it's quite nice, the centers in this sugarcane fields, which these sort of undulating hills, which there's a lot of nice mountain biking and running and all these fun things there. So the shape of the canopy was supposed to kind of match the hillsides which are around the center. So that's the one which is the feature canopy. And then down below on the bottom right, there's the stage canopy, which is the bulk canopy. And that, the function of that is, well, that was very, very functional. So the purpose was literally to keep performers dry when they play their nice instruments, and for acoustics, to make sure that the sound coming out there, you don't get too much on, because there's a parking structure just to the right of the screen. So you want to keep the noise of the parking structure out, but you want to spread the sound nicely to the stairs where the different performances can take place. So just very quickly, you can see these are initial architectural drawings. So this feature canopy had this nice sort of like wave, and the stage canopy had a more sort of conventional barrel vaulted look. Both of these canopies, the architect wanted a sort of triangulated look from a visual point of view. Structurally, from our point of view, I was quite happy about that, because there's a bunch of advantages in triangulating a structure, especially a grid shell structure like these. And when I say grid shell, I just mean a single layer of steelwork, not a 3D truss, and with moment stiff connections joining the different members. So on the outset, the conversation first is what material you're going to use for the structure. Secondly, what material are you going to use to clad it? So on the structural side, steel, obviously on this one here, these are both canopies, especially the feature canopy. It's high up, it's essentially floating in space. So you want to use a very lightweight material. First of all, it's got to be strong. The other thing which it needs to do, this is the center when it opens. Any of these big shopping centers, commercial centers, have got very strict deadlines, and there are a lot of people working at the same time trying to get stuff done. So the speed of construction was critical, and then joined with that is the accuracy of the construction. So the idea with steel was to do a lot of spend time upfront designing it, so you can create this nice form, spend a lot of time in the factory pre-making all the different beams, making sure that the quality is right, bringing it on to site, and then bolting it. So trying to do as little field welding as you can, a lot of bolting, and to make sure that what you designed is actually what ends up being up there at the top. And the main reason for that is, one, structurally, so you know how the thing's going to perform. Actually, three. One, structurally, so you know how it performs. Two, that you can build it accurately. So that's really important, because some of these things, like for example, on the stage canopy, there was acoustic panels. So a lot of these things you want to try to pre-make the cladding as much as you can prior to the steelwork arriving. And because we were very confident with the geometry of the steelwork, we could give the company that made the acoustic panels the drawings for the acoustic panels up front, so they could then pre-make that. So that obviously makes that the accuracy is very good. And then obviously the third thing is visual. Because it's a very strong material, you can end up getting quite small, slender elements, which then creates the sort of like chip-like profile for the main canopy. Now for the cladding, the functionality of the cladding was, primarily it's got to keep out rain, keep out water. And it's got to be efficient, it's got to be quick to install. And then the other thing is we needed to join the sheeting with other cladding materials. So on the feature canopy, the client wanted to look up and see wood. So we had these marine boards with wood panels underneath, but between the top of the steel and the underside of the sheeting, and that worked very well. And then also on the feature canopy, on the stage canopy, as I said, there were also acoustic panels that had to be attached. Now because the form, and I'll talk about form just now, because these were wavy structures, we wanted to use a fairly narrow profile, which had individual halter clips. So that would work with the geometry that we had. So we were quite specific on the type of sheeting that we ended up using. I'll get into that just now. So there was mostly, from a structural point of view, it was mostly tubes, which were either round or rectangular tubes. That made up our structure. The overall project was, from what I understand, about 1.5 billion, and that's part of a bigger section which is going to unroll over the next couple of years. Obviously, our part is a very small part of that 1.5 billion. So this is just the write-up. So feel free to read it if you'd like. I'm not going to go over it right now. I'll get into the stuff which has got more pictures. Okay, steelwork. Okay, so what we had, as I said, the majority of the steelwork were round and rectangular sections. So we had the main building engineer designed concrete columns. And then our scope was essentially from the concrete columns out. So we had round tubes for the column, for the tree columns, and then we had rectangular and square hollow sections for the grid shell structure on top. You can see the grid shell structure's it's made up of triangles, and breaking up those triangles, we had infill purlins. And the reason for that was because we were putting the plywood boards on. The width of the plywood boards dictated the purlins that we were using. So when we were looking at the structure, we were trying to look at the width of the individual sheets, as well as the boards, as well as the structural efficiency to figure out what our module size was. And I'll talk about that a bit more just now. As I said, cladding, we ended up using Novatex 440 for the roofing. We were actually originally going to use Ziptech products, Ziptech 420, but there was supply issues, so we had to change fairly late in the game to Novatex 440. And the coverage area, there was a lot of sheeting on this project, but ours was obviously just focusing on these two canopies. Okay, so steelwork. So how it worked from the steelwork framing. So as I said, leaf structures, that's us. We were the design build subcontractor. So we did our own engineering in-house, as well as with Novum Structures, which is a sister company of ours, which is an overseas company. Then the steelwork was made both by Novum Turkey, and then the local steel, and that was all the rectangular sections, and all of the columns, front tubes, that was by Churchyard locally. So, and then again, so from a detailing point of view, the same thing. It was a combination of Leaf and Novum, and then Churchyard. So it was a nice collaboration. So just getting into the details of some of the framing. So you can see this is the main feature canopy. So, you know, like if you look at the top right-hand picture, so that's a section view looking the short direction. And there you can see it's just a tipped, it's got I think a 7-degree slope is what we put on it. If you look at the elevation on the bottom left, which is the long elevation, you can see it's like a wavy form. And then if you look at the plan view, you can see that we've taken this grid and we've rotated it. So to kind of create that architectural form, we had a sloped, wavy, rotated geometry. So then because what we were trying to make it, the main reason for doing that is because we wanted the sheeting, the individual pans to slope straight down. We didn't want to bend the pans in the strong axis. So the pans went straight down, but in order to create that slight wave, we did at every fifth pan, we introduced a slight bend. So we could create and it was quite a gradual bend. But it was within the limits of the sheeting, and it was a way that we could use regular sheets for the cladding. If we didn't want to try to make, if it was too curved, we would have to use either glass or individual smaller panels, like aluminum panels, which would have cost a lot more. And also, I think the advantage of using the long sections, it's much easier to waterproof. So steelwork, the upper grid was 200 by 80 rectangular tubes. Each tube had a custom cast end adapter, and then we would bolt that to a machined node, which is a chunk of 355 steel, which has been special CNC machine based on the geometry. Every node, every tube was different. And then this floating chip was supported by 28 steel tube columns. Those are made by Churchyard, and then those were supported by those 5 main concrete columns, which the building engineer provided. So just kind of working from the top down. So on the top right, you can see that's the actual grid shell system. So it's got the tubes. The tubes have got rectangular holes, so we can then get a chain drive in there, and we can torque the bolts. So they've got 2 M24 grade 10.9 bolts, which have to be torqued. And that was a big part of the quality control, is making sure that the bolts are torqued enough that we have a full moment connection. When I say full, you know, when we calc it, we do allow some softness, because it's not a fully welded connection. It is bolts. And even though it's mostly stiff with these grid shell structures, because you've got lots of these connections, you know, if you don't model it correctly, you can have quite serious issues with compound failures. So we have to be very careful that we get the right, not just torque on the bolt, but actual tension in the bolt itself. So we've got a specialized load cell that we use for the project, where we can apply a torque with a torque wrench through the chain drive to a bolt, and we can measure the tension in the bolt. And then we do that at the beginning of every day, so we can make sure that we get the bolts torqued right. And then moving to the left, the grid shell was then supported with pin connections with these long columns, and then the long columns were field welded to embedded plates, which were cast into the concrete. And you can see the embedded plates were made up of, we had a sleeve that would weld onto the embedded plates, and then we can slide the column into that, so we can theoretically get the adjustment that we need. I'll talk more about that just now and the challenges. Obviously, from the analysis part, so you can see because on the top left, that's just a stress diagram of the roof. Because it is a fully triangulated moment connected grid shell, it's quite stiff, but you can see there's you know, where the tree columns hit the structure, you get kind of higher bending moments as the tree columns want to push through the structure. So when we spend quite a lot of time looking at the geometry and trying to get the tree column locations spread out, that we get even support along the grid shell. And then on the bottom right, you can see just, you know, stresses in the tree columns themselves. And you can see later in some of the pictures, obviously the longer columns are going to have higher loads and they're going to be bigger. So we ended up having two size columns. And again, like most things structurally can be simplified into something simple, because I think most structural engineers like myself enjoy simplicity. So you can see that when you're looking at deflections, it's either on the bottom right, it's a cantilever. On the left, it's a spanning beam with 3 supports. So just again, looking at deflection limitations. The bowl canopy was quite a lot easier from a structure. It was supported on the 2 ends with 2 supports, and then at the back we had 2 extra columns that's provided support. Obviously, the front couldn't have support because you want to be able to look out and see through it, but it was made up with the same system. So also 200 by 80 tubes with M24 high strength bolts. So this is just talking just a little bit about how the connections are joined. So what we would do is, you can see there's where you've got those access holes, and then on the image on the top left is from one of our drawings, where you can see the chain drive comes into the bolt. I've got one sitting here somewhere, but the chain drive goes in there. You apply a torque at the top. So what the team would do is they would first get the tube, make sure you get the right tube in the right place, the right way around, and you use the right node. Once that's in there, you would put the tubes in. You would put the bolts in. Not full torque, just partial torque. You'll get a big section placed, and then you would do the final torque on it. In terms of modeling, yeah, so the whole structure was 3D modeled. So what we've actually got some very nice in-house software that we've been working on for a long time, which can, once we've got it modeled, it fully generates all fabrication drawings. So it spits out hundreds of tube drawings and CNC node cutting files. So there's no, I think on these structures, because everything's so similar, it's very easy to make mistakes if it's a manual process. So that part is all automated. The time from the modeling is where the arms of the supports hit the underside of the node. All of that is still manual 3D modeling. But at least on the grid shell self, that's we've got that nicely automated. The other thing you can see, so in the image in the yellow, the writing, there's a couple of things. One is, every beam's got a number and a direction, but it's also we've also got the geometry, the XYZ of every single node at a specific height, and that's needed for the survey, so we can make sure that we are accurate with our installation. Okay, so on the cladding side, metal cladding, so Leaf Structures, we hired for 4 seasons roofing to get the profiles and to install them. So as I said, we were going to use Ziptech, but we ended up changing to Max Steel, so that they're the suppliers of the sheeting, and then 4 seasons installed the sheeting for us. So this is just looking at the profile of the feature canopy, and you can see what we've done there is we've got straight segmented pieces, and how we did the geometry was we took the width of the sheets, and we said, okay, we're going to have five sheets per bay, and then we looked at how much these things can rotate. So that's how we could create that undulating form out of straight sections. So with the install, what we ended up doing on that is, so it ended up going in parallel with the boards. So they would the plywood boards, the marine grade plywood, they were already cut in the correct width, and they had notches, so they could fit nicely over each other. So they would put boards on top, then put a weather layer, and then put the sheeting on top of that. So that process actually went very quickly. They didn't need any scaffolding. They just need to get the material onto the roof. So it was a very efficient process. There was also just around the edge of the canopies, we need to have a gutter made. So we ended up getting a fiberglass profile made, which I think added quite a lot of value to the project. So just quickly I will not talk too much on the fabrication. As I said, so the left picture is from the factory in Turkey where they make the tubes, and you can see there it's just a standard rectangular hollow section with these custom cast adapters. There's a lot of different adapters that they keep in stock. And then the pictures on the right show the tree columns, which were made locally by Churchyard, with the sleeve component that can slide in and out. Okay, so the installation part. So the simple part, I'm going to show you first the simple part. That's the stage canopy. So this is how theoretically it should work, and then I'll show you what some challenges just now. So stage canopy, you get everything laid out nicely. You then bolt them together with some scaffold as you go. Once everything's bolted together, so that one we could lift the whole thing and then put it into place. One of the reasons for doing that was because they were still building the concrete work that supports that structure when we were doing our steel work. So by the time they were finished with their concrete work, we said, okay, cool. Now we can now put our structure on there. So that worked out very well. One of the challenges, and I'll talk about it just now, it rains a lot in Durban. We had a lot of rain on this project, so it was that was definitely one of the challenges that we encountered was lots of rain and mud. So talking about challenges, so I would say the installation of the feature canopy was probably the biggest challenge. And I think I like this picture because it shows the mud, and this was when it was quite dry. If it rained every second day, and every day it rained, everything became a big pile of mud that you couldn't really work. The other problem is that because this was an entrance to the shopping center, we had so many other contractors and subbies trying to go in and out while we're trying to work. So the challenge with the install is because this thing's floating in space, there's no real reference point. With the stage canopy, it's easier because you can measure the concrete, you can get a fixed point and work from there. When it's floating in space, there's no fixed point. So what we did wrong from the install is we got the tree columns installed based on a survey, but there was a misinterpretation of this survey. And that was something that went even though we had all the BIM models and it wasn't properly interpreted through us, our fabricators, our installers. So basically the tree columns weren't totally right. So we installed that one section that you can see there. And we said, okay, we must get it surveyed prior to continuing. So when we surveyed that section, you can see, so with the 4 points that we show there are the 4 corners of that one section that we installed. And you can see it minus 120 mils, 213 mils, 77 mils. So that whole section wasn't at the right angle and it was twisted, which means if it's twisted, it means as you try to build this thing, it's going to fit. It's not going to fit because your tree columns need to still tie into the structure. So after a while on site, sweating, figuring out what the problem was, we found what the problem was and it was a survey interpretation problem. So we took that thing down, and you can see one of the problems with these long tree columns, if you are 3-4 mils out at where you weld it onto the concrete column, by the time you get out the sort of 8-10 millimeters, you're 600 mils out. Obviously, things don't work when you're 600 mils out. So what we ended up doing is we got the contractor to build a very sturdy scaffold which had peri props in place at specific locations. We actually gave them the survey points for those props. So before we even lifted the structure, they got those props to exactly where we needed it. So we could lift the section, place it on those props, then survey, make sure they were right. And once that section was right, then we installed the tree columns. So you can see there in the picture, you can see the peri props have got the pads on. It had been marked out exactly where the node sits. Once it's there, they could adjust, and then they could get the tree columns in. By doing that, we spent about a month and a half getting stuff wrong. Once we got the system right, we installed that whole canopy in 7 days because we knew exactly what was wrong. So then it was a lot easier. So now from then we had 7 lifts, and we could install from there. And once the structure was all in, and all of the columns were then fully welded and checked, we could then drop the scaffold, and then obviously the other parts of the building could continue. So the benefits of steel, I think I've already spoken to it, but it's one of these as I said, I can't think of another material that we could have done this with, just due to the complexity of the geometry, due to the site constraints, and due to the need for tolerance. So as I said, I think it worked. As I said, we had challenges with the install, but none of those challenges had actually anything to do with the steelwork. It was the challenges of the interface with the concrete and the misinterpretation of the survey. So I think it went, but the actual steelwork, every beam was exactly right. There was everything fit exactly as it should have, which was good. From a QA point of view, I didn't talk too much. I don't want to talk too much on this, but there was a lot of QA/QC processes going through the design, through the fabrication, through the installation, checking welds, making sure the bolts, every bolt was tightened, making sure that the sheeting was correctly applied, that the wood was correctly applied. So there was a lot of process that went through that, and it's just on the paint. So it was all of the steelwork was galvanized. The tubes were electroplated, and then we had a carbothane final coating. The paint was primed on the ground, and then the final coat was once it was installed. I mean, I think what we're proud about this project is it's a privilege to be able to be entrusted by the architect and the owner to try to bring their vision to life. And I think it's always nice, like the two left pictures. Obviously, the top left is the original rendering, which was years ago, and the bottom left is what we ended up building. And it's always a nice feeling being able to create something which I think looks very similar to the original intent. And I think that's done through collaboration of working with a lot of people from different skill sets, on site, off site, and trying to collaborate. Especially, I think the collaboration on this one is particularly meaningful to me because there was problems on site. So whenever there's problems, people are pointing fingers, and I think we managed to, as a team, keep the mind focused on trying to fix the problem. And I think when it was fixed, then it was fixed quite quickly. So I think that's always a nice thing, because construction, as we all know, there's millions of variables, and you can try to get everything right, but there's always something that slips through. And I think the way successful projects are ones where those things, if they do slip through, you can find them, and as a team you can fix them. I think I've just got a short video to play quickly of the project. That's it. Thank you.